Okay, this is example 3.4. And in this example, we're putting everything together. We're putting together work, force, and kinetic energy. Suppose you hit a nail with a hammer and drive the nail 5 millimeters into a wooden board, which is in figure 3.7. If the hammer's head has a mass of 0.6 kilograms and it's moving at 4 meters per second when it hits the nail, when it strikes the nail, what's the average force on the nail? So let's draw a little picture here so you can see what's happening. We have like a 2x4, it's a piece of wood. And then we have a hammer. So this hammer is smacking a nail, right? So there's your nail into the wood, bam, right? One smack. And what they do is they tell us that the distance that the nail goes in, this distance is 5 millimeters. It only goes in about 5 millimeters. Okay, that's the distance that it goes in. Okay, they give us some information. They tell us the mass of the hammer is 0.6 kilograms and it's moving at 4 meters per second squared. So here's the logic we're going to use. They're asking us for the force on the nail. Now, we do have a relationship between force and distance. That is equal to the amount of work, right? That's what we looked at in the previous section. So the idea here is that when the nail is pushed into the wood, it takes work to make it go down into the nail. So we want to find out essentially how much work we did by moving that nail. Now, the problem is that we don't know the force, right? The work, we don't know that, but we also don't know the force. We just know the distance. We know the depth that it went in, which is 5 millimeters. So we know D, but we don't know W or F. So we're kind of stuck here. I mean, we do know that if we're trying to find the force, which is what they're asking us for, we could divide both sides by D, and that would tell us what the force is. So all we really need is the amount of work that's done. But again, we don't know the amount of work. So here's what we're going to do. We know that the hammer is transferring energy into the nail when it strikes it. So how much energy does the hammer have when it hits the nail? And that's the amount of energy it can transfer into the nail. So what we're going to claim is that the amount of work done to move the nail into the wood is equal to the amount of energy the hammer transfers into the nail, right? This is essentially, you know, it's a mechanical thing, right? You have this hammer, it has energy because it's moving, it hits the nail, transfers energy into the nail, right? Boom, the nail goes in. So how much energy did this hammer have when it hit the nail so that it can transfer the energy into the nail and move the nail and do work on wood? Well, that's the kinetic energy. So for the hammer, the kinetic energy is equal to its mass times its speed squared over 2. And then, so if we know that, then we can say, look, the amount of work that was done on the nail is equal to the kinetic energy. So the work is equal to the kinetic energy of the hammer. This is the nail. Okay. All right. So let's figure out what the kinetic energy is. Well, the hammer has a mass of 0.6 kilograms. It has a velocity of 4 meters per second. But we got to square that, right? mv squared divided by 2. Okay. So if we take 0.6 and we multiply that by 4 squared over 2, well, that would be like 0.3 times 16. So that would be about 4.8. The units would be kilogram meters squared per second squared. Why? Kilogram meters squared divided by second squared, right? So about 4.8 joules really is what that is, right? A kilogram meter squared per second squared is a joule. So now we'll say that the amount of work done on the nail is equal to the kinetic energy. So that's 4.8 kilogram meters squared per second squared. Okay. Now we want to find the force on the nail. The force done on the nail is the amount of work we did on the nail divided by how far it moved in. So the force would be W over D. So that would be 4.8 kilogram meters squared per second squared divided by the depth. Now they put it in millimeters. Okay. 5 millimeters, millis 10 to the minus 3. So 5 times 10 to the minus 3 millimeters, right? 5 millimeters is 5 times 10 to the minus 3 meters. Notice how often that material from chapter 1 comes up. Milli, 10 to the minus 3, centi, 10 to the minus 2, deci, 10 to the minus 1, kilo, 10 to the 3, mega, 10 to the 6. Okay, so 5 times 10 to the minus 3 meters. And what happens in terms of units is that one of those meters cancels with that one down there. So we had meters squared over meters. So that's just equal to meters. So now it's 4.8 divided by 5 times 10 to the minus 3. And I think that comes out to about 960 or so. Let's see, you double it. So 960. And then you got kilograms. You got one of the meters left over divided by second squared. Hey, guess what? Kilogram meter per second squared. Not a joule, but a Newton. So that's 960 newtons force. Okay, so this one involved kind of a little bit of logic that you might want to watch this video a second time to see my logic. The idea is we want to know the force on the nail. That's equal to the amount of work done on the nail divided by the distance that the nail moved, which is the 5 millimeters. We don't know the amount of work. So what we have to do is we have to figure it out from the hammer. The hammer has kinetic energy. It has 4.8 joules of kinetic energy. That 4.8 joules is transferred into the nail, does work on the nail to make it move 5 millimeters. So once you get the 4.8 joules from the hammer, you can use that as the work done on the nail. You've got the depth of the nail, the height or the distance that the nail moved. Now that ratio at W over D, that is going to give you the average force.